So in class we took these notes, finishing out the bottom of page 11 and then doing the double replacement notes at the top of page 12. And you're going to want a periodic table for these. And page 11, we had started by talking about decomposition reactions and breaking apart our compounds into separate elements. And at the end of page 10, we had talked about how to put together products into a compound in synthesis reactions, how we have to check charges to put them together. Well, both of those skills are actually going to be necessary for these single replacement reactions, because if you remember, single replacement reactions are the reactions where we have an element and a compound that's replaced that element is going to replace one of the other elements in that compound. So we always have an element and a compound on each side. So we're going to be predicting these products, trying to find that single element that's going to be alone now and write the formula of the compound that's going to be created. And you'll see in this section there are 6 reactions right underneath this first top kind of notes section. And then there's a line of text, and then there's 2 more examples. And that's because, if you remember back from our original types podcast, there's technically 2 slightly different kind of flavors of single replacement reactions. So we're going to have to predict their products a little bit separately too. But it's the same general process. And the biggest difference comes down to what type of element that single element is. And this top part is going to be where that single element is a metal. And the key idea here is that that metal is going to replace another metal. So metals have positive charges. And in a compound, and I mentioned this when we were talking about synthesis reactions and making those products, we always have a positive ion at first before the negative ion. So here, when we are dealing with metals, metals are going to replace other metals because they have the same kind of charge, so they're going to be able to replace each other. Once we notice that our single element, like the magnesium here, is a metal, what we need to be thinking about, is going and finding the metal from this compound, seeing who's going to try to replace who. And so we know the metal should always be the first thing because it's also going to be the thing that has the positive charge. Positives are always before negatives in compounds. Positive then negative, every single compound. So magnesium is going to try to replace iron, but it's not necessarily able to. Just like with people, if we're trying to have magnesium replace iron, they're kind of fighting over who gets to be with nitrate. Well, nitrate kind of gets a say in things, and nitrate is going to want to make a change and have a reaction happen if the new element that it's going to be with is more stable, more favorable. It's going to make it more happy being in that new compound. Just like with people, we're not going to make a change, break up with someone, make a new compound, make a new couple, if it's not a better choice. If it would make us less happy or worse, we're not going to make that change. So the elements have a list of kind of who's hot and who's not in terms of the periodic table. And the higher up an element is on this list, the more likely they are to replace the other elements that in a single replacement reaction. So you do not have to memorize this list. It is on the back of your periodic table, or you can always flip back here to page 11 and check it. But when it comes down to this problem, magnesium and iron are fighting over nitrate. Who gets to be in that compound with nitrate? Well, let's check what nitrate wants. Let's see who's higher up on our list. We have our magnesium here and our iron down here. So magnesium is higher up. So magnesium is who nitrate wants to be with. And since magnesium is not currently with that nitrate, they're going to make a change. They're going to get together. So I usually start these products by writing the compound because that's the part that's going to take the most effort. And remember, when we write a compound, we have to check the charges of those elements. Magnesium's a +2, nitrate is a -1. So since they're not equal and opposite, we are going to have to cross-drop reduce those numbers, which means that 2 is coming over onto our nitrate, and that means we need to put the nitrate in parentheses. So that is magnesium nitrate. All together and happy now, but we can't forget about iron. Even though iron is single now and separate, it needs to be included in the reaction. And just like in our decomposition reactions, when we create a single element all on its own, we need to check our diatomics. Those Brinkelhoff elements that can never be on their own. And there is no iron in this list, so iron is fine being by itself, so we just leave it as Fe. And we've just predicted the products that we would make here. Now, in this next one, copper's trying to replace zinc, and if we look at them on our list, zinc is higher up on our list. So zinc is the one that is going to be part of the compound. Zinc is going to get the girl. But zinc is already in the compound. Zinc is already with chlorine. So chlorine wants to be with zinc. Zinc is higher up on their list, but since they're already with zinc, we're not going to see a reaction happen. That's exactly what I would expect you to write down. Just because nothing happens in a test tube or in a beaker doesn't mean we don't write anything down for it. You need to show me you know no reaction will happen by writing no reaction. Blank means I don't know, but NR, or no reaction, is the shortest, simplest way you can tell me I checked and I know nothing's going to happen. This stuff could sit in a beaker all day. You could even heat it up, do crazy things to it, and these two things will not react because chlorine would rather just stay with that zinc. So in this next one, start trying to figure out who's trying to replace who. Magnesium is trying to replace hydrogen. Now, it might throw you off a little bit because hydrogen is a non-metal, but it is still over here in our list of metals. It's just in parentheses to show, kind of tell people, yeah, it's over here. It does technically have a positive charge like the rest of these metals, which is why we include it. Notice it is still at the beginning of this formula. So it's the positive thing, chlorine is the negative thing. So magnesium's going to try to replace hydrogen. And if we check, hydrogen is here, magnesium is up here, magnesium is higher up. So magnesium's going to get the girl. Magnesium gets to be in our compound with that chlorine. So we're going to put them together, check our charges just like before. Magnesium's +2 is still crossing over. It's just this time it's only crossing over onto the Cl instead of that big old nitrate group. And then hydrogen is forced to be out here in single, but hydrogen is a diatomic element, so we need to give it a 2 to keep it company. These diatomic elements can never be by themselves. So it doesn't mean they always get a 2. Notice in HCl, it was just one H and one Cl because those charges meant we just needed one of each. But it's not alone. It's got a Cl buddy keeping its company. Diatomics are the ones that can never be completely alone. If they're trying to be forced to be alone, like here, plus hydrogen, just H on its own, no other element to keep it company, we have to put that 2 on it. So, I did these top 3. I want you to try these bottom 3. I know that you might struggle a little bit with writing some of these formulas, but at the very least, we should try and start underlining or kind of drawing some lines, trying to see who's trying to replace who. And we should definitely be able to figure out when there's no reaction versus a reaction. And at least one of these is going to be no reaction. But even on the ones that do have a reaction, if you're struggling on writing these formulas, at least get the right pieces together and try and get them in the right order. Check those charges if you know them, if you can, and get the positive thing first, then the negative thing. And if that's as far as you can get, I can help you finish up and put them together into formulas. But I want you to try this process. Use the activity series. Figure out who's trying to replace who. Can they replace them? And if so, remember, whoever's higher up gets the girl. Whichever element is higher up in the list is the one that gets to be in the compound. So, at the bottom of the page, we have this slightly different type of single replacement reactions. So, what's different here is that instead of having a metal as our single element, we're going to be looking at a halogen, which is that second to last column in the periodic table. All of those elements can replace other halogens if they have a higher reactivity. So it's just a non-metal here. Technically, there are reactions that we could give you that are not just halogens replacing other halogens. There are other non-metals that can replace each other, but the chemistry of those starts to get a little bit tricky, especially in predicting which one is more reactive. So we're just going to stick with this one column, this one family of elements, halogens, and since they're not on the activity series, we have to use their position in the periodic table in order to tell which one is more reactive. And just taking a quick peek at our periodic table to kind of remind you of what we're looking at, back in Unit 3, we learned that fluorine had the highest reactivity out of all of our nonmetals. So especially within its own group, it's the most reactive out of all of them. So it's almost like this column of elements on the periodic table is its own little mini activity series. So back in our packet, I might suggest that you write those elements in the same order that they are on the periodic table over here next to the metal activity series we have, just to have a non-metal version as well, a halogen version. And just like our metals, the higher up it is, the more likely it is to be able to replace the other halogen that is in the compound. So, same exact process as with our metals. We just have to realize when we find that non-metal as our single element, we have to go and make sure it's replacing the other element it's like, the other non-metal in that compound. So we need to ask ourselves, can fluorine replace chlorine? Which one is higher up? Well, fluorine is at the top, so fluorine can replace anyone. And so yes, fluorine gets to be in the compound. So we're going to put that F at the end of the compound, just like the Cl was. If we double check our charges here, that +1 and -1 cancel out. So our formula here is just NaF. And then don't forget that that Cl is now single, and it is a diatomic, so it gets a little 2 on it. In this next one, single bromine is trying to replace part of this compound. Who are they trying to replace? Well, the fluorine. Can bromine replace fluorine? Nope, fluorine is at the top of the list, and bromine is definitely below it. So fluorine's higher up. Fluorine gets the girl. Fluorine gets to be part of the compound, and it's already part of the compound. So what do we write? No reaction, or NR at the least. Now I do want you to add one last example here, and the reason I wanted to give it to you is kind of twofold. First of all, I wanted to remind you that in all of these examples, 1 through 8, on this whole page, we had started with the single element first, and then we wrote the compound. And in general, I wrote the compound first and then put the single element after. But I just kind of wanted to remind you that these can be written in any order, as long as these reactants are both an element and a compound before the arrow, then that's single replacement, no matter whether it starts with the element then the compound or starts with the compound then the element. So, single replacement, because I have a single element in a compound, and I always focus on the element first, even if it's written second, because that being a non-metal, that being a halogen, tells me which part of this compound is going to be trying to be replaced. So F is going to try and replace Cl, and just like in example 7, it can. So we're going to predict that aluminum is now going to be with fluorine, and if we check our charges, +3 and -1, mean that that is going to be AlF3, and our Cl is now single. And I could have just as easily written that out and been like, oh yeah, fluorine can replace chlorine, so chlorine is now single, and then I have my AlF3 as my other product. So those reactants and products can be written in either order. It doesn't really matter as long as they're both there and you check charges when you put them together. The other thing I wanted to point out to you is notice how in this AlCl3 turned into AlF3 when they replaced each other. They're practically identical. And both of these halogens are diatomics. So it's almost like we just took that reactant side and straight swapped the Cl and the F. And that's because they're all in that same column of the periodic table. They all have the same charge. So they're going to make the same kinds of formulas when they come in and make compounds and elements as well. So even though these are a little bit harder in some people's opinion because they're not on the activity series, it kind of pays you back. Writing the formulas and balancing them is a little bit easier because they are so similar to each other. So I don't think that either of these versions is necessarily harder or easier than the other. All the single replacement are pretty similar, and you mostly have to remember to check and see, can the single element replace the element that's it's most like in the compound. You got to remember to check if it can be replaced, because it doesn't always happen. So flipping over onto page 12, we're going to talk about double replacement reactions. And something weird happened with the spacing of things on these last couple of pages. And the word double replacement reactions was actually at the very bottom of the last page. I would really recommend you go ahead and write it at the top of page 12 here, right above this generic equation, so that when you are working in your bracket later and need help predicting products of double replacement reactions, you can actually find this chunk of notes and look back at these examples. So write double replacement reactions up at the top of the page, and you may or may not need to write down that light blue note that these always react. This is really just a reminder that unlike the single replacement reactions where we have to check the activity series, we do not have to use that here. We just do the reaction. All of these reactions, in fact, every reaction we assume can occur and will occur other than single replacement. So we only need to make sure we're getting the right things broken apart and put back together. Now that little red note off to the side is something that I do want you to make space to write down. We touched on this idea a little bit when we talked about applications, and we mentioned that redox reactions are reactions where the oxidation number or charge of our elements changes during the course of the reaction. And we learned that every type of reaction is a redox reaction except for double replacement. So even way back then, we told you double replacement charges don't change. They're the same before and after, but it didn't really mean much to you. That is actually going to be a really important idea here as we're working out these examples, and especially number 2 and 3. So write that down, and I'll mention it, bring it back when it becomes more relevant again. So remember, double replacement reactions are reactions that start with 2 compounds. So these compounds, the analogy I had used before was the wife swap, where they're each going to be breaking up into pieces, separating from each other, and coming back together to create some new compounds. And I want to focus on this generic equation for a minute here, just to help make sure we understand the pattern of how things break apart and come together, because that's going to help us predict these products. And I also think a little bit of color can sometimes help us visualize this better, easier. And I'm also going to remind you that a compound, like all of these compounds we're starting with and ending with, is always going to have the positive ion first and then the negative. So even though I don't know what elements they are, I can tell A is a positive element, X is negative, B is positive, Y is negative. And that is going to stay true on both sides of the reaction. And so if we're considering this as the wife swap, where these A and X are breaking up, B and Y are breaking up, and they're going to switch buddies, notice at the end, after that arrow on our product side, A got with Y. A is not going to stay with X. A and X are breaking up, and it's going to come over here and try and get with part of this other compound. And the part it's attracted to is going to be the Y part, because it's the part that has the opposite charge. Positive things are going to be attracted to negative things. So the first part of that first compound is always going to end up getting with the second part of the second compound. And then that leftover B and X are going to come together to make another compound. And here it's important that it's BX, not XB, because we always put the positively charged thing first. Even though X is written before B in this reaction, when they come together to make a compound, it's going to be a BX compound, not XB. So this generic equation is almost like a recipe for how to break things apart and put it back together. So let's look at this first reaction. I always start by trying to kind of divide up my compounds, figure out where they're going to break up. And with something like NaCl, that's pretty simple. The Na and the Cl are breaking off of each other. Over here in AgNO3, we've got 3 elements, but we're still only ever going to break it up into 2 parts. And NO3 is one of those special groups. It was called nitrate. It's on the back of our periodic table, and we never break up one of those groups. It's easier to remember that when we have those parentheses around it, like in example number 2. But hopefully we're starting to get used to some of these special groups that we've been seeing, especially when they're written for us. So let me know if you're struggling to figure out where to break it up, but that's always my first step. Break it up into its 2 pieces. And then we're going to take the first piece of the first compound and the second piece of the second compound, the positive and negative pieces from those opposite compounds, and put them together to make our first product. And anytime we write formulas of compounds, we have to check their charges. And luckily here, Ag is a +1 and Cl is a -1. So those charges just cancel out, and AgCl is our first product. And then Na and NO3 are the leftover pieces, and we're going to put those together into our second product, making sure to put Na before the NO3. And if I had forgotten when I was checking my charges, that's a nice time to make sure I have positive then negative. But once again, my +1 and -1 charges cancel out, so NaNO3 is my other product. Now in this next example, as we start breaking things up and putting them back together, Pb is going to be getting with our I. And as we check our periodic table charges, we can find iodine's charge, but we don't know lead's charge. Lead is in that weird area of the periodic table down here underneath our staircase, anywhere between that staircase and that second column, including our lead, where they can have multiple charges, where the charge is not necessarily going to match the charge you probably have written up top. So because of that, we're going to have to look at the charge of the lead before the reaction, because like I pointed out and asked you to write down before, charges do not change in the course of a chemical reaction. So if we need to figure out what lead's charge is here, we just need to go and check what was the charge of lead back over here in this other compound, because it will be the same charge when we see this lead. Now, so I know this part of our Unit 4 was not really your favorite. A lot of people kind of struggled to look at compounds like this lead nitrate and figure out what kind of lead nitrate it was. Remember, we had to put that Roman numeral in the middle, and a lot of y'all thought it was pretty hard. But this is actually going to tie in with the next skill that we're learning. And it does still kind of start with breaking it up and remembering, even though we don't know lead's charge, we always know the charge of the thing that it's with. This nitrate group, according to the back of our periodic table, has a charge of -1. And there were 2 of those nitrates there together balancing out whatever lead's charge was, because the total charge in this compound has to be 0 for it to be a stable, happy, finished compound. So I just need to ask myself, what is lead's charge that would cancel out this 2 -1s from those 2 nitrates? Well, hopefully you're realizing that would have to be a +2 charge. So that means that our lead over here is still a +2 charge, because charges don't change. And if that's a +2, when we cross drop reduce, that 2 is going to be crossing over onto the I, and we don't really write 1s, but the 1 from the iodine could be crossing over onto would be, and we just don't write 1s. So PbI2 is our final formula. And one more thing that we're making is going to be made out of that K and that nitrate getting together. And just like up above, our nitrate is a -1, and K is in the same column as Na, though it's still a +1, so just KNO3. Not too bad, I hope. Just more practice writing formulas. You just got to follow that pattern to get them together and know your charges from this periodic table. So now I'm going to do these next 2 examples, and there's nothing really new in them. I just want you to see me work out 2 more examples. If you have any questions, if at any point you're like, where did that charge come from? Why did you put this with that one? Or how did you find this formula? Please ask me in class if you didn't already take the time to. But I just want you to see a couple more examples where this happens. I'm not going to say, okay, now you do it all on your own. So We're going to break up our elements and then start putting together the first element from the first compound with the last element from the last compound. Then we check charges on the periodic table. Unfortunately, iron is not something I know the charge of, so we're going to come back and look at iron in this compound. And iron is with sulfur. We know sulfur is a -2, so iron has to be a +2 if there's just one Fe and one S canceling each other out there. So iron over here must still be a +2 charge, which means when we cross-drop reduce, that's going to become FeCl2. And then the other compound we make is going to be made from that S and that H. We need to make sure to put the H before the S, so we have the positively charged thing before the negatively charged thing. And when we check those charges, this time sulfur's -2 is going to be crossing over onto our H. There we go. And that is all written, all of the correct products together. Now, I haven't been balancing any of these, and they would need to be balanced. Don't let that throw you off and make you think that we're making a mistake because I've got 2 H's there and just 1 H there. We can balance this whole reaction by putting a simple 2 there in order to get 2 H's and 2 Cl's to balance everything out. So we're not focusing on that part right now, but that is something you're going to be doing in the next chunk of problems. So breaking up these 2 products, making sure to leave the O and H together. That's our hydroxide group. And that H is going to be getting with our OH. AH and OH, first thing from the first compound, getting with the second thing from the second compound. We check those charges, +1 and -1. And so those are happy and stable together. And we can move on to making our second product, which is going to be made from Na and Cl together. And checking those charges, +1, -1, works out really nicely to just be NaCl. Now, technically, some of you might be looking at this HOH and kind of wishing that we could put those 2 H's together. And you can, if you'd prefer. And what you'd get if we move that H over, combine it with the other H at the beginning, because it is a positively charged thing, it should stay at the beginning, H2O, that's water. So we actually talked about this type of reaction, or the application. It is a double replacement type, but this is an acid-base reaction. We learned that acids start with H's and bases end with OH's. So if we have something that has an H at the beginning mixed with something that has an OH at the end, then that is what we call a neutralization reaction, an acid-base reaction. And we were mostly focused on just identifying them. So we were focused on finding that acid and that base. But an acid and a base, we did say, will always make water and a salt. And the reason for that is because if I have a double replacement reaction that always has one thing that starts with H and one thing that ends with OH, those 2 pieces are always going to be coming together to make our water. And then whatever is left behind, whether that's chlorine or bromine, sodium or potassium or anything else, makes some other ionic compound. And that's all that a salt is some ionic compound. So that's kind of the proof, that's kind of the reasoning behind why those acid-base reactions are always double replacement and why they always make water and salt. So at this point, what we need to do is start predicting products on our own. And so you are doing what seems like a lot, 12 through 15, but we're only doing the odds. So it's really not that many problems, and most of them are pretty spread out on the page because you're going to be writing out these reactions. Notice that here I give you directions on how to do this. A lot of people start trying to jump into this reaction first off, and you should look at those reactants, but the first thing you should do is ask yourself what type of reaction could happen with these current reactants. You should be able to tell what type it will be, and then once you find your type, that's going to tell you how things are going to move. Because a synthesis reaction, we're just going to shove everything together into one compound. But I can tell you right now, question number 1 is not a synthesis reaction. So I'm going to do something completely different with number 1 based on what type of reaction it is. So make sure you're finding those types first, then come back over to actually complete the reaction, and don't forget to balance them. Most of these aren't going to be impossible to balance. The real work is on predicting the products and writing those products out correctly. So if there is one that you're thinking is impossible to balance, there's a good chance you might not have written those formulas right. And you can either double check the formulas or on your own or with me to make sure the formula and equation is right so you don't get stuck balancing them too bad. Now, just like before in our synthesis reaction, as well as in single replacement, when we're making new compounds from elements, then we might need to know the charges of some transition metals. So these don't count for double replacement reactions because these, in double replacement reactions, the charges are the same. So like we saw iron before had a +2 up in reaction number 3 at the top of this page. But in other situations, iron would actually prefer to be a +3. So we're going to use these charges for the weird transition metals in synthesis and single replacement reactions only, which is another reason to definitely make sure to figure out your type. So go ahead and circle all the odds, maybe put an X through the evens just to make sure you don't accidentally spend your time and energy on those, because I am looking for the odds only. The evens are good practice, but I would prioritize starting with those odds.